So the last talk of the morning is going to be given by Xiangru Huang, and it's dual decomposition learning with factorized oracles for structural SVMs of large output domains.
Okay. Hi, thanks for giving me this opportunity to do this presentation. So this work has some relation with the work that Inderjit just talked like hours ago. So this is also a sparsity-based approach, but it works on structural SVM problem instead of a multi-class SVM problem. So this is a joint work with Ian, Kai, Rohan, Chia, Pradeep, and Inderjit. Okay. So let me give a outline of this presentation. So I'm going to introduce the structural SVM problem. I'm going to introduce what's the intrinsic challenge there, and I'm going to give some key idea about how to solve that problem, and then we derive our algorithm and give some deeper explanation. Then we show some experimental results there. So first, the introduction to structural SVM. So basically, we know that for classification problems, we have to learn a function that maps from a set to another set. But for a structural case, we actually we map the features into a structure output. So we are assuming that there are some structural dependencies there, and empirically, this structural dependency will help us to get higher accuracies. So the first example task is sequence labeling. So it's famous in natural language processing, where you have a sequence of feature vectors, and you're trying to map each variable you're trying to give each variable a label. And usually the case is you have a large vocabulary size for natural language processing. Maybe I should introduce. So this is basically for structural SVM problem, we're dealing with factor graphs. So typically in this work, we dealt with unigram factors and bigram factors. So unigram factors connects with just one variables and gives scores to that specific variable. And bigram factors connects two variables and gives score for any combination of the two variables. So this is basically the case. For a multi-label classification problem, basically we're assuming that there are some dependencies on the appearance of each simple label. So we're actually predicting a set of binary classification problems, and we're assuming there are some correlations between them. So given this task, there are some challenges here. So the first thing to note that is because the factor size is like for a bigram factor, you have actually the factor size is actually a square of the unigram factor k factor. And if you're dealing with n-gram factor, you actually raise that size to n. So if you have like over thousands of labels for possible labels for each variable, and you raise that to n, it will quickly goes out of your control. So, and another thing needs to mention that is for the optimization technique, in order to get a decent direction every iteration, you actually have to do a map inference on the factor graph, and that's very expensive. For the sequence labeling case, you actually you can use like fast algorithm because there's no loop. But for like harder, more complicated graph, you actually the inference takes even more complexity there. So people are actually trying to avoid this kind of exact inference algorithms. So they did some kind of approximation there. For the community of natural language processing. But of course, the various kinds of approximation usually downgrades the performance for a considerable amount. So in this work, we're trying to not use approximation, try to give the best accuracy we can and still and make the training time more reasonable. So the key idea of this paper is that a structural oracle that we use to find the descent direction is too expensive. So the first thing is we use the standard technique, dual decomposition, to reduce the structural SVMs to multi-class SVMs with respect to each factor. And we softly maintain the consistency constraints between all the factors so that we can treat each problem as independent as possible. So the techniques we used in this paper is active set and Factorwise oracle, which is to be compared to structural oracle, and sparse message passing. So first let's talk something about Factorwise oracle. So the good thing about dual decomposition is that after decomposing the structural SVM into a set of independent multi-class SVM, we can actually adopt any existing technique that can be used on extreme multi-classification problem to extend that to structural case. So in this paper, we actually adopted the previous approach that worked on the PD sparse solver introduced by Interjet. And so I'm not going to talk about this. And for bigram factors, we actually use priority queues to speed up the search so that we can find the descent direction much faster. So typically, if we don't use Factorwise oracle, we have the complexity that equals to the domain size of a bigram factor. But now that since we use active set and we use Factorwise oracle, the complexity reduces to the product of active set with respect to each variable. So it's much more cheaper. So let's try to do some derivation about the algorithm. So the original structural SVM problem is just like this. So you have a regularization, you have a loss. So we use the structure hinge loss, which is also called max margin loss, I think. So it's basically the same thing. And we use dual decomposition to decompose. Basically, we just take the dual of this objective function and decompose that into a summation with respect to each factor. And note that there's a consistency constraints there. So previous approach that used structural oracle explicitly enforce this consistency constraint. So they have to use structural oracle to look through the factor graph and to find a feasible direction, but also the optimal direction. So it's quite hard and expensive. So we're not going to do that. Instead, we're going to use the augmented Lagrangian method that tries to relax the constraints here to be a penalty term, and we update the multiplier as the standard ALM algorithm. So, and after that, what we need to do is basically alternating between the dual variables and the multipliers, and until we get converged. So there are some experiments here. So let's see, for Chinese OCR, optical character recognition. So we have 12,000 chains. Each chain have an expected length 14, and we have feature size of 400. the number of possible characters are over 3,000. So note that the bigram factor has a size that equals to 3,000 squared, which is about 10 million. And note that decoding algorithm is basically a Viterbi algorithm because we don't have a loop in the factor graph, so we can do exact inference there. But that's still, the Viterbi algorithm takes the complexity of this order, like this 10 million order. So note that the red line is our algorithm. The green line is the algorithm that Simon, the approach I just said. So it used the Viterbi algorithm, so you can see that there's a huge speed up here. And things become more dramatic here. If you, for this multi-label classification problem, because now the factor graph has loop, so in order to do an exact inference, you have to perform a linear programming at each iteration. And note that linear programming actually takes hundreds or thousands of iterations to converge to give you a good descent direction. So this would lead to a huge cost in time. So note that this green line is much more worse in this case. And something funny about this is actually, we actually want to try the data set that's called EuroLex, which have number of labels equal to 3,000 or like 4,000. But we can't do that because actually the evaluation of the test error also needs this exact inference. And this is too expensive, so we can't perform that. But I think our algorithm, given a good, fast enough inference oracle, can actually be evaluated on larger data set and give better speed up there. So thank you.
Thanks again, and we have time for a few questions.
So there's a whole line of work on. There's a whole line of work on the dual decompositions for structured prediction in the natural language community. Andre Martins is the name comes to mind, but also Terry Koo and others. Can you compare what you're doing to their work?
So for training case, there is no existing approach that uses dual decomposition, but also
that's actually not correct.
Oh, no.
I know this works, so I can tell you that.
But that doesn't converge to the global optimum. It has some. Yeah, I think that's what I believe. But of course. So the other approach is that even if you use dual decomposition there, each iteration still takes here. So each iteration still takes this yi, y1, y2 complexity there. So this for the extreme class case, this is still too expensive to perform. So our next contribution is to reduce this complexity with respect to only the active set. Empirically, the active set is for a data set that has over 3,000 classes. The active set size is barely exceed 30. So you have like 30 square instead of 3,000 square. So it's a good speed up there. Yeah, and another thing is also there are approaches that use dual decomposition, but because this work that from PD sparse is original to us, so I believe that there's no other people that have adopted this speed up for the unigram factor.
Okay, let's thank the speaker again.